Welcome, my dear colleagues, ladies and gentlemen, to this first session where we present highlights of the three projects as mentioned. Please hold your questions till the Q&A session at the end of this session at about 11, if I'm not mistaken. 12:30. We have more time. That's Moxy will kick off now. Will be presented by three of the PIs, three cornerstones of the project. First speaker will be, I will introduce them all at the same time. First speaker will be Ilaria Bonaduce. Professor Bonaduce is Associate Professor of Analytical Chemistry of the University of Pisa, and her research explores the chemistry of organic materials in paintings and archaeological objects. And she aims to reconstruct in this artistic practices and understand material changes. She's the first speaker, as mentioned. Professor Geert van der Snickt will be the second speaker. Geert has a master in conservation restoration and a PhD in chemistry, based on research in Professor Janssen's group, the Access Group at the University of Antwerp. Geert is currently a research professor in heritage science at the same university in Antwerp in the Faculty of Design Sciences. Then, last but not least, is Noura Rahbani, who has a PhD in electrochemistry from the Université de Picardie, Jules Verne. And, well, inspired by her research topic for her PhD, developing iron-based electrolytes for redox flow batteries, and also being aware of the environmental and technological challenges brought forth by the energetic transition, she decided to move into life cycle analysis and joined WeLOOP in Lille. And she will talk about LCA, the LCA part of the Moxy project today. So can I give the floor first to Professor Bonaduce?
This is not working. Okay. Okay. Good morning, everybody. I'm Geert van der Snickt, as Klaas just introduced me. First, before we start, it's important to mention that this project is very much the baby of Thomas Markevicius and the RUPT group in Ghent. But since Thomas is already speaking this afternoon, Ilaria and I were, let's say, appointed to give this presentation, which we gladly accepted. And we will present this. We present this a bit like the news is done with two news anchors. And usually you have a charming lady and a less charming man who takes turns according to the topic, and that's what we'll do. And then somewhere in the middle, we'll go to the young reporter in the field who will give her expert opinion on LCA. So that's how we'll try to do it. So there we go. So Moxy is a project which is basically about radically new methods of cleaning artworks in a greener way, and is using atomic oxygen, which we usually abbreviate to AO. And the proposal was a direct response, was a direct response to a series of very extreme and dramatic events that unfortunately the conservation field is more and more frequently experiencing, such as here, like the big fire in the National Museum of Brazil, or the Notre Dame in Paris, or more recently, the Palisades fire in LA that narrowly missed the Getty Villa. These are images we all know from the news. And I think these fires and these extreme events, climate events, they become more and more frequently, as it said there. In 2023, 135,000 acres were burned down in 12 days in more than 4 Mediterranean countries, and at the same time also devastated museums and sites in one of the Hawaiian islands. And much more fires are to be expected, unfortunately, because this is a quotation from a paper by Falke, who defined that up to 48% of the sites in Europe are in a high-risk field for, or the range for climate events. And many others, it's not just fires. We know there are a lot of climate-related threats, such as these are a few images from a new type of mold outbreak, which is seen in museums, which are even well controlled. So it's not happening only in museums where there is that are, let's say, struggling with maintenance, but even in very good museums, there are new kinds of molds surfacing, which are probably related to the warming up of the climate. And these events, what they all have in common is that they change the rules for us in the heritage field dramatically, because this is what we are used to. This is a conservation studio where the Kikirpa is treating the Van Eyck Ghent altarpiece. This is what we're used to. That is objects which are prone to slow and gradual decay. Treatment is done every 50 to 70 years approximately. So the Ghent altarpiece was treated in the 50s. Sorry, now again in the 2020s, and probably it will need attention again, let's say, by the end of the century. So we're used to that. It goes slow, so it gives us time to do research, to allocate budgets for the treatment, and everything can be prepared. But a fire or other climate-related events, they are the opposite. They're sudden and they're extreme, and in a few hours, thousands or even 10,000s of objects are damaged or even destroyed. So it's something completely different. This is here. This is an example of the Herzogin Anna Amalia Bibliothek, where in 2004, 180 books were damaged, and it took up to 14 years to treat everything. So it's necessary, or it's clear that we need new tools, new solutions for this, and especially since I think we are starting to consider our cultural heritage as a critical resource that also is not only just nice to have, but it generates also wealth and income for the European community. And of course, it's not only fire, but you have floods, you have rising of sea levels, you have hurricanes, humidity, etc., etc. I'm sure you're all familiar with that. And what I would like to stress here is that Horizon Europe is the only channel which, in my opinion, is capable of developing or boosting this kind of new solutions. Because if we look at project budgets from national funding agencies, they're usually too limited. They give often, you can get 1 PhD or maybe 2 PhDs or postdoc. But we need this large consortia, this interdisciplinary consortia, to start up this very complicated new solutions. And one of the new solutions was atomic oxygen, was developed by Moxy, and this was done by connecting the dots between the heritage field and research which is done at space agencies. And I think it was Thomas who actually connected these dots. And with research in space agencies, for Moxy, I mean what you see here. This is the low Earth orbit simulator, where they simulate the conditions to which spacecraft are prone to when they are launched into space. And in that environment, there is atomic oxygen. And what is atomic oxygen? Atomic oxygen are single oxygen atoms. And we know oxygen from the air, but there the oxygen is bonded to another oxygen atom. But these are single atoms unbonded, and they're very reactive. They react with whatever comes on their path. And so they erode spacecraft when they go into space. So for space agencies, it is a real threat. And the AO is something you find in, let's say, the low Earth orbit. Okay, and in the 90s, there was already some pioneers from NASA, which you see here, Bruce Banks and Sharon Miller. They already set a kind of proof of concept by showing that AO is very good at removing carbon-based contaminants, and they had the idea to try it on art. As you can see here, this is the bathtub. It's a painting by Andy Warhol, which at some point a lady in the museum felt it a good idea to give the painting a kiss, probably because she liked the painting. So there was lipstick on the painting, and they managed to remove, as you can see there on the right, the lipstick with atomic oxygen. So one of the very few projects which can say that it all started with a kiss, which is very remarkable, I would say. Okay, so, oh yes, one thing I have to mention that this AO, this proof of concept and this prototype was of course not something which can be used in a museum or a conservation setting, was just to show that it works. And so this is where Moxy comes in. This is our consortium. You see the photo of the kickoff meeting in Ghent with all the partners on there. I'm not going to go into details. I don't have the time for that, but there are these are the work package leaders from University Ghent, Eindhoven, Antwerp, Pisa, Amsterdam. And then there are some museums involved. The museum in Copenhagen, the Moderna Museum in Stockholm. There is ICOMOS represented, and then there is a company WeLOOP for the LCA calculation. Okay, and then I give the floor to Ilaria.
Thank you. So, good morning to everyone. So, at the start of the project, to make sure that we were developing a technology that was meeting real needs in the field, we decided to start with an elicitation study. Now, elicitation research is a type of research that uses bottom-up methods to gather input and salient information from end users and stakeholders. So this is very much used in several fields like social sciences and psychology and anthropology, but it's never been used to support the development of a new tool in the field of cultural heritage. So we started with some consultations that was carried out during a couple of events, and since the very beginning of the project, we started with some interviews with end users. There were 20 experts coming from 5 continents, coming from different backgrounds, different expertise across the world, and we had the chance to discuss with them what would have been important technological features for our new technology, and also discuss with them what would have been important for them to import this technology and start using it. We also had the chance to discuss the concept of sustainability in cultural heritage, and it was very interesting to see how different this was across the different continents. And finally, also, it was important to highlight which were real and met needs. And a common discussion was soot from fires. It was a very difficult material to remove. And the fact that there are materials that are matte, porous, and fragile, which need new tools in order to avoid mechanical contact. So starting from there, we started the implementation of the project, and I would like to summarize some of the main achievements of the project, but also to show you what we've got ahead of us and what are the new possibilities that could come from the work that has been done so far. So at the beginning, the first challenge for the University of Ghent and Eindhoven was to develop the Moxy system. So to develop a system that was capable of delivering the atomic oxygen that is normally present in low Earth orbit onto the surface of the object in order to clean it. And this device had to work at ambient conditions in the presence of air, and also allow a fine control of cleaning parameters for tuning power and flow of oxygen and so on, and also be small and compact so that it could be transportable and suitable, at least at the beginning, for simplified flat surfaces, and also to start treatments of real objects. So this was the challenge, and what you can see here is our systems in action during the cleaning of some soot from some surfaces. The system produces a flow of atomic oxygen that is transferred to the surface of the object through a nozzle. And what you see here is a section of this nozzle. So basically, we have a mixture. I don't see it. So we have a mixture of helium and molecular oxygen, which are delivered through a plasma to the surface of the object. The plasma is a radio frequency plasma that enables the dissociation of molecular oxygen into atomic oxygen. And this flow is protected from the external air by a flow of argon, is shielded. So basically, the object is in contact with this flow of atomic oxygen, but is not in contact with the plasma of the nozzle. And what you see here is one of the very first prototypes with Anton, our coordinator, and then also you see the machine that is available in Ghent, and this is the latest prototype that has been developed and is now available at the University of Pisa. So what makes the atomic oxygen that is produced by Moxy so different from the atomic oxygen that is present in low Earth orbit, which is so aggressive to spacecraft? Here is a list of differences, but what I want to stress is that the atomic oxygen in low Earth orbit has a very low density, but is also collides with spacecraft materials with a very high kinetic energy. This means that it's capable of carrying out an unspecific erosion of the materials that it encounters. On the other hand, atomic oxygen from the Moxy system has got a high flux and is also a low kinetic energy, which means that it will react chemically with the materials that are sensitive to its action, and the action is going to be fast because we have a high flow of atomic oxygen. And also, what happens is that the material to be removed will be converted in carbon oxide, carbon dioxide, and water. So there are going to be no residues on the objects and no production of substances which can be toxic for the environment or for the operators. It's a selective action because it needs the material to be sensitive to the action of the oxygen. And so it's incredibly efficient, for example, for the removal of soot, but is extremely sensitive to the materials that constitutes the majority of works of art. And we will come back later on with that. And so,
Okay, thank you, Ilaria. So if we then come to I'm going to put it a bit higher. We come then to the actual cleaning tests, and so which you see here. The cleaning tests, we developed a methodology for that, and we divided the testing in 3 phases. As you can see, we started with an explorative phase, then followed by a methodological testing phase, and finally a validation. So the exploration phase is all about selecting. And this is a very chaotic phase where we tried as many materials as possible to see what works and what not, preferably from substrates and materials that are real objects, to check what would work or not. So we come to a selection of priority materials, and then we move to the methodical testing, where we're going to test very systematically, in a very tedious way, let's say, all materials, but based on mock-ups to see how they respond to the AO cleaning. And this is mainly about optimizing, so finding the optimal parameters for the cleaning. Finally, we move on to the validation phase, and this is again a reality check. So we return to the, let's say, real objects, the real life heritage objects, and we do testing on them to see if what we found in the second phase actually makes sense. Does it still work if we move from a mock-up to a real object? And also we do a benchmarking, because a benchmarking is actually, this is what you see here, it looks like this, is actually a comparison of AO cleaning with more traditional or other methods which are used in the field, such as laser cleaning, soft particle blasting, micro vacuum, etc. So all the techniques that all the conservators know, because we do not only have to prove that it works well, we also have to prove that it works better or faster or more efficient than the other methods. Otherwise, it's no use to go to this very high-tech instrument. So all of that is quite a lot of work, a lot of experimenting, as you can consider. And from the second phase, or for the first phase, we selected 4 priority materials where we are focusing on. That is paints, textiles, plaster, and paper. These are the main materials that we looked into in a systematic way. And we added some promising cases, but from which we know that they're interesting, but that we do not have the time to go at length into the testing. And these were plastics, natural feathers, gypsum, silver, and lead white. And I give you some, I cannot, of course, go into detail of all these materials, but I give you some impressions of the cleaning effects. So here you have paints which were mainly looked at by University of Pisa and University of Amsterdam. And you see here a slide from Katarina's work, where you see tests on mock-up which has been suited both on impasto and normal. One of the paints which was very challenging was the acrylic paint, because the soot got really embedded in that paint, especially after artificial aging. And nevertheless, it was possible to clean it without big damage, although the surface was a bit mattified, so it was less shiny than before the operation. But nevertheless, acrylic paints are a real challenge. This is silk. Silk was an interesting material to focus on because it's organic and it's very fragile, so it's hard to clean. So it's a good, it would be a good thing for the field if you can clean it with AO. You see some examples here. This is with the soot, and this is the pristine, so without the soot. And here you see by increasing the power, you see that we come to something which is very close to a very pristine surface. So the AO cleaning works well there. We also looked at paper, as you can see here, which is again an organic cellulose-based material. And then we have plaster, on which it also worked very well. Now, as a general conclusions of all these tests, and I'm oversimplifying things here a bit because I cannot go into details here, we don't have time for that, but we managed for all our priority materials to find and optimize parameters and find like a safe window. By tuning the instrument, we find a window of parameters that can be used to clean in a safe way. Does not mean that it's always the best solution AO, because conservators know that each object is different, it has a different history, there are different soiling materials on top. So they always test things, but what we can do is we can give the conservators a window with parameters that's, that will, but they know that they will work and they will be relatively safe for the object. And it's possible to clean these objects with a higher efficacy, which means that we can remove more soot and more soiling in a more efficient way, so in a fast, relatively fast way. So this is a bit the outcome of all our painstaking systematic testing. And then I show you this slide because we also worked on feathers, as I told you, and feathers are, of course, the perfect, we included it because it's the perfect showcase material. Everybody, you don't need to be a scientist or a conservator, everybody can imagine that feathers are very fragile and very difficult to clean if there is soot on them. And so we did some experiments on that, and you see it works relatively well. Also, because feathers are part of, let's say, sometimes part of indigenous cultures, and not all indigenous cultures accept that their objects are treated with all materials. So in this case, we do not touch the object with AO cleaning. So this was a nice outcome, I think. And now it's back to Ilaria.
Thank you. So in addition to understanding how efficient is atomic oxygen in cleaning and what are the performances and the validation and the comparison with other techniques, we started with a very big concern. Atomic oxygen is very reactive. What about the oxidation of the substrate, of the material that we want to clean? And so for this reason, we went through a systematic investigation of its action of a series of materials, and we selected some materials that are very common, like oil paints and acrylic paints and paper and plastics and textiles and feathers, in addition, of course, to soot, in order to expose them to the action of atomic oxygen and understand the changes at the chemical and physical level. The starting point is that atomic oxygen action goes through a chemical reaction, which is oxidation. And this can occur following several pathways. But what is very important to keep in mind is that in order for the reaction to occur, the material has to have a reactivity towards it. So not all chemical functionalities will be reactive towards atomic oxygen. What does it mean? If we take, for example, a surface of a polymer, means that there will be areas that are not sensitive to the action of oxygen, while there might be areas where there are functional groups that could react with atomic oxygen. So when we expose our system to our flow of atomic oxygen, when the atomic oxygen collides with those parts where there are the reactive sites, then reaction may occur. But when the atomic oxygen impacts those areas that are inert to atomic oxygen, nothing is going to happen, and the atoms of atomic oxygen will recombine to form molecular oxygen. What does it mean? Let's take an example of an oil painting. If I take an oil painting that is 3 months old, so it's very new, very reactive, we will have, here it's in yellow, quite a high reactive surface, quite high surface reactive to the action of atomic oxygen. But when the paint ages, these reactive sites will decrease in size, and they will decrease their reactivity with time. So at the end of this experimentation, we can say that if we use the right techniques, we can detect some chemical changes and physical changes in the materials. But we can also say that these changes depend on the material, but they also depend on the age of the material. And the more aged is the material, the less sensitive in general is to the action of atomic oxygen. If we compare these chemical changes to those that are caused by other systems that can work non-contact, like laser cleaning, usually they are comparable or even less. And what's very interesting is also the fact that after a few weeks or a few months, we cannot detect any more chemical differences between the samples that have been treated and those that have not been treated, meaning that the chemical changes that are caused by the atomic oxygen are negligible with respect to those that are caused by natural aging, which is very important because it means that our art substrate in general are quite inert to the action of atomic oxygen. Soot, on the other hand, is very different because it's a very porous material and it's got a very high concentration of reactive sites, which means that when atomic oxygen gets in contact with soot, the action will be immediate, and so it will be converted into gaseous substances, mainly CO2 and CO. So this is very important for us, because there is a very high selectivity of atomic oxygen towards the contaminant and not the substrate. And now I will pass it to Noura.
Hello, everyone. So our part in this project is to really try to define what makes a technology green. And our approach at WeLOOP is to do what's called a life cycle assessment. So a life cycle assessment is basically an environmental impacts assessment where we model any product or service based on all of the input and output consumables and energy that occur throughout a product's lifetime. So for this, we look at the full life cycle of the product, thus the name LCA, which starts from the extraction and processing of the raw materials to the fabrication of the product, to its use, and at the end, to its end-of-life treatment. So in the case of the Moxy project, we started with this life cycle assessment of the device and its use. And from this, we were able to get quantifiable numbers of what are the different impacts on different environmental categories. The most well-known is climate change, but there are much others, like impact on toxicity, on resource use, on water use, on human health. Then the question was, how do we use these results? So first, we organized an eco-design meeting with the consortium members, where we were able to identify how the environmental hotspots identified in the study were able to influence decision-making choices in the development of the device. And then there was the other question of how do we compare this device to what's already there? So then there was the question of benchmarking, similar to in the testing of the device. And this is where really a lot of practical constraints in conservation came to light and took a big role in the study, because to make a meaningful benchmarking, we need to check apples with apples. So the idea here was that we needed to define specific use cases for different types of substrates that are contaminated with soot, to be able to build these different scenarios, cleaning scenarios, and then we do a model for every different cleaning scenario for a given sample, using all of the possible contactless and contact cleaning methods. And then from this, we're able to do a benchmarking, which could be used for decision-making in terms of which method to use. But we were also able to extract from this results for the different cleaning methods, what are general recommendations for a better, more sustainable use of a cleaning method. But all of this only takes environmental impacts into account. And for the Moxy project, we really wanted to go beyond environmental impacts. So for this, we did what is called a full life cycle sustainability approach, which also includes economic and social aspects. So the same life cycle concept of the different life cycle stages and the impacts on the different life cycle stages could be applied to the other two pillars of sustainability. So for the economic assessment, we did an economic life cycle assessment, which is called life cycle costing, which takes into account all of the costs that go into not only making a method, but also using the device. And for this, we applied the same benchmarking scenarios that we used for the environmental assessment. And we also did a risk assessment for the use of critical raw materials. And this part of the assessment was really focused on seeing if the continued use of the Moxy technology is viable economically. And then the the social assessment came with a different goal. And this is something that's very particular to cultural heritage, because if we want to only look at environmental considerations, one could argue that the most sustainable, and heavy air quotes, approach is to just not clean it all, because everything's going to come with an environmental impact. So the idea here is to do a social life cycle assessment, which takes into account the different stakeholder groups that could be affected in the different life stages of a product. And the idea here is to show that when we're dealing with decision-making in cultural heritage, just taking environmental and economic impacts into account is not enough, because this is an unrenewable resource. And we are actually organizing a webinar where we go more in depth in this sustainability assessment of the Moxy device, and also the assessments that were done for the other projects. So if you're interested in that, scan the QR code and you will get some more information. This is our next news report, and there's also my email if you want more information.
Okay, sorry. We're finishing, yes. Okay, so the outcomes of the project very quickly. Of course, we have trained several postdocs and PhDs, as you can see here. There was a lot of communication and dissemination, 42 presentations at conferences. Big one was Technart, where we had a separate session, which is important, some images there. But another specific outcome was the patent, which is applied for on the nozzle system, which Ilaria discussed, which is basically taking up Moxy 4 to 5 levels in the TRL. So we're now at level 6 to 7. And then there are a few byproducts, which I think are also important. And these byproducts, I call them also bycatch. They're not specifically on atomic oxygen. They're in the sphere of conservation, and they really move the field forward, I think. And one of these bycatch things are, for instance, the reproduction of soot, which we looked very much into, because it's not so easy if you are comparing cleaning tests to produce soot-covered mock-ups in a very reproducible and comparable way. And we developed a protocol and a soot drum to be able to do that. So that's now possible. So all conservators can use this. There is Marta, who developed a machine learning approach for evaluating cleaning efficiency. So to isolate soot particles on, in this case, soot particles, but can be also other dirt, on the substrate to really quantify the cleaning results, which is also an interesting thing for the field. And then we developed a methodology for comparative cleaning tests, because you have to go to a certain line of thinking and a design of the research, which has never been published before, I think. And so we made this methodology, and that will be published soon. And then a final word on road mapping, so the future.
So, to conclude, there are still several things that potentially can be done. One of them, for example, is bringing our Moxy system to ATRL 9, for example, but there are also other options. One of them would be to upscale the nozzle. At the moment is a point action, so it's very slow. But for example, we could make it bigger, most likely like a line scan. And what you can see is that there is an incredible, a substantial decrease in time in the treatment of the material, and also a more efficient use of helium. Another upscaling that is possible, for example, is the replacement of helium with other gases, which would be very important in terms of sustainability. But one thing that we're going to test in the following weeks is its use for the removing biological contaminants, for example. And then there is the possibility of integrating our system with other technologies. One of them would be, for example, the modification or activation of gels or solvents for modifying their cleaning action. Another possibility would be to use it to activate or modify the surface that we want to treat. For example, paper can be, the wettability of paper can be changed with atomic oxygen, which means that we could be able to treat hydrophobic stains that otherwise are very difficult to treat. And there are other possible modifications, like with gypsum, we can make changes which would have an impact not in the field of a cultural heritage, but outside, for example, in dentistry, where we want to, or bone grafting, when we want to produce new materials with different characteristics. And finally, to integrate fully the Moxy system with the other conservation strategies. So I hope we convinced you that the Moxy atomic oxygen is a new tool in our toolbox, and which is potentially very interesting for non-contact, non-mechanical cleaning action of very sensitive surfaces, which could be very interesting in terms of the development of the implementation of sustainable cleaning strategies. And thank you very much.